So part 2, I'm going to talk about manifold learning, and this is a slightly idiosyncratic view on what I want to tell you about it, as you'll see. I was instructed to do this and not to keep doing that, so I'll try. So the central dogma for geometric data analysis is that the data consists of a finite sample from some low-dimensional geometric object. And I'm being deliberately vague here about what low-dimensional means and what geometric means. We do know now what we mean by sample. So it's a metric measure space. It has some additional geometry, and I don't want to say what it is yet. But one kind of thing that people often imagine is that, in fact, it's a manifold, or it's a compact Riemannian manifold. And let me say a little bit about what that means. But of course, the goal is going to be to recover something about the geometry or the topology of this from finite samples. OK, so what's a manifold? Just to tell you, so the way to think of this, I mean, if you know what this is, great. But the way to think of this, if you don't, is that this is a place where you can do calculus. And what does it mean to do differential calculus? It means to know what a tangent is. That's it. And I will say that, and apologies if you work in this area, I think there are very few ideas in manifold learning, and essentially everything boils down to estimating tangents, almost everything. And so, so this is an important thing. And so the idea is that at each point of the manifold, you have, for curves that go through that point, you have a vector space where all the possible tangent vectors can lie. And these are organized in some nice way so that nothing really screwed up happens as you move around in the manifold. And so I don't want to say how you organize it, but so let's just think of a function from points to vector spaces. And it's the best linear approximation at that point. OK? And the dimension of those, if this is a manifold, the dimension of those vector spaces is the same as you move around. And I will say that, I said something earlier about not believing the manifold hypothesis. My experience has been that it is not right that dimension stays constant if you move around in actual genomic data. So I don't know what it is, but it's not something that has a constant dimension. It's not a fractal either, I don't think. And so it's not like the dimension is like a half.
Actually, elaborate a little bit on this point. So how did you come across the counterexamples of it?
I mean, you just try to start estimating. So estimating dimension, and I'll say something about this, is hard. But you start doing it, and you just don't get the same numbers as you move around in the data set. And they look really different in ways that could be an artifact, right? It's hard to know, but, So this is, you should think of this as like, I'm sorry this is being recorded, but what can you do? You should think of this as like vague prejudice. I don't have a theorem here. It just doesn't smell right to me. And it's one of these things like, years ago I was at this talk that Mike Hopkins gave about his work on the atom spectral sequence or something, and someone asked like, how did you know this thing was going to be 0? And he was like, well, you wander around in the desert long enough, like you know where things are. And and like that's the level of like I don't have a theorem. It just doesn't look right.
Does the religious objection extend to assuming that the data lies in a finite union of manifolds? Which is what I usually think of.
Yeah, that's better. I don't think that's right either. Because
plus noise, of course.
Yeah, but plus noise. I mean, one thing that's hard to say, of course, is as soon as you add ambient noise, everything starts to sort of look smoother and smoother, right? And so, maybe you can't really tell that it wasn't a manifold, even if it wasn't. And maybe, you have to ask, can I really,
so it's
can I see singularity?
It's not clear what difference it makes.
Yeah, so there's a different question of what difference it makes, but the fact that the dimension is changing is a pretty big deal. And I think if you look at the curvature, I spent some time trying to estimate curvature. Estimating curvature is hard. And I'll say why, but if you think about curvature, that also looks wrong. And so now that we're talking about this, let me just say something, which is that I think the way you should think of this, the best way I can think of this comes from thinking about something like Morse theory. And the idea of Morse theory, right, is that you have your manifold, you have your space, and you have a function to R. And you start looking at that function, you look at its critical points, and its critical points are where things change. And what's the topology of what's happening between the critical points? They're paths. They're some kind of flow lines of some differential equation. And I think that the right way to study whatever the geometry is on genomic data is to understand what the moduli spaces of flows between whatever the right analog of critical points is. Do I know what that looks like or what structure those moduli spaces should have? No. But that's what I think you should do. Anyway. OK, but coming back to manifolds, we have these tangent planes. And, so we have examples, right? Euclidean space is a manifold, the sphere is a manifold with the plane rotating around on it, toruses, hyperbolic planes. And these all look different. Oops, wrong button. So really we want a little bit more. And so we're going to assume that we have what's called a compact Riemannian manifold. Compact just means it lives in a bounded region. Again, so that's not a restriction at all, really. And Riemannian manifold, like I've written down these complicated things, but let me just say, all it means is that you have inner products on each of these vector spaces. And if you have inner products, you have volume from the determinant, and you have length from the norm. And so now, as soon as I have that structure, if I have tangent spaces and I have an inner product, I have a metric. And what's the metric? I'm at a point. I want to go that way. I take the derivative. So now I get a little tangent vector, and I take a step. And I measure the length of that step. And now I'm in a new tangent plane, and I take a point, and I take a little step, and I measure the length of that step. And I take the limit as these steps get real small. That's the metric. Okay, you walk through the tangent planes. And what this tells you, of course, from an algorithmic perspective, is that all manifold learning algorithms that do things like estimate the metric or even try to get coordinates, they all amount to estimating the tangent planes somehow. And there are different ways you can think about that, but they all do something like that in order to do things. Okay, so manifold, even with the manifolds are hard, right? Like things you might want to know. You might want to know the dimension. You might want to know the curvature. You might want to estimate the geodesic distances. If you're ambitious, you want to know the whole second fundamental form, which is some tensor which tells you lots of things about the curvature. And how are we going to do this? Well, a really nice way to think about it, this is not the only way to do it by any stretch, but a nice way to think about it is that if you take Bishop-Gromov theorems, you take a Taylor expansion of the ball volumes. The first two terms, the lowest order term, looks like r to the d. And so here's a way to, here is a maximum likelihood estimator under certain hypotheses. And this, I think, is written up in Levina and Bickel, although the idea in the computer science literature is much older. You take a point, you start blowing up a ball around it. Now, what's the volume of a ball? Well, in 50 dimensions, like, I don't know, but it's proportional to r to the 50. So I take the log, and I do a regression, and the slope of that line, that's something like the dimension. Okay, that's a dimension estimator. If I look at the next term, you can estimate the curvature if you can get sort of ratios of estimating the ball volume to the ball volume in Euclidean space. Now, good estimators of these things depend only on this intrinsic dimension. Bad estimators depend on the ambient dimension, which is embedded in something. But these are hard. Dimension estimation, I'm complaining that it looks like it changes, but if you start looking in the literature, no one can estimate dimension effectively over dimension 8. You have immense amounts of bias that turn up. And curvature, if you ever tried to estimate a ratio, so I worked on this with my postdoc Abby Hickok, and what she found was that for an intrinsic thing, so you don't imagine there's an embedding. If you imagine there's an embedding, you can do better because you really can estimate more. You can use the embedding, and I think Smito worked on this, and you can do a little bit better. But if you don't assume that, and it's just the metric properties and ball volumes, on a good day, we can get the sign of the curvature. And I'm not talking about the sign of the curvature in complicated data. I'm talking like, take a monkey saddle, where like analytically I know what the curvature is, right? These are hard problems, even if we assume the manifold hypothesis.
So sorry, what's the reason that it's so bad when the dimension is bigger than 8? I mean,
you just don't have enough points.
There's a sampling question.
Yeah. You basically don't have enough points to get a robust estimate. But also, this kind of volume estimator, because of concentration of measure, this kind of volume estimator gets harder and harder to make sense of. So, but nonetheless, we still try to do it. So I was saying something about this before, but what's the idea of manifold learning? The basic primitive is you build a k-nearest neighbor graph, or you fix epsilon, and you take a graph on your data points where you connect the edges that are of distance, length, and epsilon, and you weight them by the distance, and then you take the path metric in that graph. And what is that? That's a discrete version of this thing I was acting out earlier where you walk through the tangent planes, right? There's this slogan, short distances are good and long distances are bad. What that means is short distances probably lie in the tangent plane, and you can understand them, and long distances don't. And you can imagine this. If you have something like this, I want to walk along like this. I'd rather not have a shortcut like this. Okay? And, and this is basically the underlying idea for this really is the only idea in isomap, but it's the underlying idea for LLE and UMAP. Like all these things look like locally estimate the tangent planes and then do some global optimization to sew them together. And, and that's how everybody works. And you can sort of do this. And I will say that this, I talked at the end of the last talk about Scott, which is an alignment algorithm for doing like batch correction.
By the way, I mean, this is a matter of estimating the metric in the C0 sense, and to be Gromov-Hausdorff
Yes.
close to the
Yes.
sample,
Yes.
not in the C2 remodeling.
Correct. Correct. This is not a smooth approximation. Yes, absolutely. Yes, I talked about this paper, Scott, and in order to do these Wasserstein matchings, you have to do dimensionality reduction. And a nice way to do it is to do something like this and do the Wasserstein distance on this sort of manifold approximation to whatever your metric is. And that turns out, in that kind of case, it turns out to work okay. And again, you can ask questions, which I'm not going to say a ton about, or really anything else about how fast this converges. And what you can prove, again, is that the rate depends on something, as you would expect, depends on something like the intrinsic dimension, but also on something like some bound on the curvature, or in the injectivity radius, right, about your manifold. And what's happening if it's like all crinkly, you need more points than if it's flat. Okay, no surprises. Okay, so I've said a bunch about concentration of measure. Here's a sort of a summary of the issue. So if your dimension is large, geometry as we know it does not make sense, right? If you're in 2 dimensions and you pick 2 random vectors, 2 random unit vectors, they're never orthogonal, basically. If you pick 2 random unit vectors in, R50 or R100, I think the probability is something like 2/3 that they're orthogonal. If you pick it in R500, the probability is like 1. Okay, that's bad. Right? From the perspective of thinking about geometry, that's bad. And so none of these constructions that we do mean anything. Another version of this is this thing that Shmuel explained, which is that if you take uniform samples on a sphere, as the dimension increases, the probability gets very high that they lie around an equator. In fact, any equator, by this easy symmetry argument. Another way of saying this is that the volume of the unit ball lives on the boundary, almost all of it, if you're uniformly sampling. So these things don't mean anything. And I don't think I'm going to explain Levy's lemma, but this is a way of saying this sort of more precisely. So this makes things hard if the dimension is at all high. And here's sort of a picture of what's happening on the sphere as the samples get closer and closer to this equatorial band. So now that was kind of a sharp transition, but let me say some words. I now want to talk about using sort of a combination of manifold learning ideas and some of these Wasserstein ideas to do something cool. For some version of cool. Let me tell you what it is. So if you have a noisy Swiss roll, I have a picture of the Swiss roll on the next slide, but just if, everyone I think knows what this is, but this is this canonical data set in manifold learning where it looks like this, right? You kind of curl this thing up, and so it's a pain because there are cross-cutting edges if you're not careful this way, and you really would want it to go along this way. So embedding this is everybody's first test, and of course it's conveniently 2-dimensional, so And so if you have one that's very noisy, all manifold learning algorithms break. They're not robust. And unless you do some kind of smoothing. And one way you can smooth is you can subsample. You can do like a bootstrap. And if you do some kind of topological bootstrap, and if you subsample, what you see is that some of the charts look good, and some of the charts have noise in them and look weird. And now you can do this cool thing where you can cluster in Wasserstein space. Right? I have a way of matching data sets, so I can cluster. And if I cluster, what I'll find is that there's sort of, the nice patches all lie in one cluster, and then there's sort of this, smeared out thing with lots of weird looking patches, and then there's kind of some schmutz out here. There's this, you can kind of tell. Moreover, and this is a particular.
I'm confused. In the Swiss roll,
Yeah.
there are lots of parts that are sort of isometric to each other.
Yes.
So when you cluster, why don't those points become the same?
Because what we're clustering is finite. They do sort of. That's what happens here. But we're taking a cluster of like a uniform sample across the Swiss roll. So when you unroll it,
Oh, so you're not looking at a chart?
no,
Or a piece.
well, it's just like one big chart. Yeah, we're not looking at little charts. We're looking at
You're
one
looking
big
at big samples from
Yes.
the whole thing, and
Yes.
then you're subsampling.
Yes.
Okay.
Yes, exactly. And another thing that's nice that I particularly like about this is that you can of course look at this and say, well, these are tightly concentrated, and so I should take that seriously. But another thing you can say is I can compute the persistent homology. And what you see is that good charts are contractible. When in this case, we know that the original object is supposed to be contractible, and so we're sort of cheating. But in any event, we can do that, and whereas things that are, in this case, that are bad have non-trivial topology. And so you can use persistent homology as a criterion for finding this kind of thing. And then at the end of the day, once you've picked this cluster, you can do an averaging in the Gromov-Wasserstein space to get a final coordinate output. And so what you get when you average these aligned things is something that looks more or less like you want it to, the sort of unrolled Swiss roll. So this is sort of...
So what do the colors mean here? I'm sorry.
Oh, it just means if you look... Ooh, do I have a picture? Here we go. So the colors tell you sort of coordinates around the roll.
Oh, okay.
And I'm
Good.
just asking, did I unfold it properly? And this is very noisy, right? These red points are noise. And now when I subsample, most of the charts have non-trivial topology. But if I use that,
When you say the red points are noise, it's not. You're sampling a bunch of points plus that kind of uniform noise.
yes, I'm not being very clear, and I apologize. I take this entire set, the union of the Swiss roll thing, which has these pastel colors and these red points.
So extra points.
Extra bad points.
Not,
And these are adversarially chosen in the sense that they are not concentrated. I just uniformly sampled these from a bounding box. They are not concentrated around.
how many points compared to the points that you sampled from the roll itself?
I think the ratio is like 10%, 15% you can deal with. More than that, it starts to become
So
difficult.
it's really adversarial. It's not noise, observation noise.
It's not observational noise. It's really like, yeah, and this is a thing that I'm interested in, which is that most geometric data analysis algorithms are not robust, right? In the sense that if you go think back to how I define the Gromov-Hausdorff distance, if I take one bad point, I can change it by a lot, right? I can change it arbitrarily. And so subsampling is a way to try to smooth it out. And that's kind of what this is getting at. Another way of saying that, and again, I think I owe this perspective to Shmuel, is that you can think about noise as like little tiny arbitrarily complicated manifolds at infinity. And those, if you don't take seriously some notion of smoothing, those can arbitrarily change what happens in any kind of topological estimator. So I'm taking subsamples from this whole thing, and most of those look crazy because of these red points. But some of them don't. And now I can try to identify, if I just do isomap on this, I get this. But if I identify the ones that look like this, simply by looking at their persistent homology or by looking at how they distribute or cluster in Wasserstein space, then I can average those ones and get something that looks like this, even though I had all this noise. Yeah.
Do you have any idea of any heuristic on how many subsamples you should be taking?
Yeah, a lot. Yeah, you need a whole bunch, right? Because you can compute, it's like maybe like a coupon collector kind of, or you can compute what you would need to have good subsamples. And if you have any size, if you expect any reasonable number of adversarially chosen points, you need a lot of subsamples to hope that a couple of them look like this. I have some picture. This is based on a paper that I wrote with Mike Mandel and Junhao Feng and Matthew Carriere. And there's a picture somewhere where I think we computed hundreds and hundreds and hundreds of these, and a couple of them were good. It's not if there's a lot of noise. If there are only 3 points, almost all the charts are good.
Right. No, that was kind of.
But it deteriorates
balancing,
fast.
Yeah. Okay.
So you're not, I mean, being robust is hard.
No, that's not a question.
Yeah, you know.
But anyway, there's this phenomenon, maybe, right, that you go ahead and do this, and it's only a small percentage that are good, but they're clustered. And
Yes.
there are sort of lots
Exactly.
of, right, as Tolstoy
Exactly.
said, there are lots of ways to be bad.
Yes.
There's only one way to be good.
Exactly.
You look for the biggest thing.
Exactly.
But
Wow,
that's why I'm asking for heuristics, right? I mean,
Yeah.
if you had some kind of understanding of
That was my question.
distribution of persistence diagrams, right?
Yeah.
And there is some interesting work coming out on that.
There is. Then you could actually probably get numbers. So yeah, that's right. Yeah.
A naive question. What if you remove all the red dots? How does isomap looks like?
I mean, it always looks like this. This is the correct answer, right? Because the idea is that the intrinsic coordinates on this thing is just, you just unroll it, and it's like, and it's flat, because you're looking at the distance along that thing. And so that always looks like this, but as soon as you add, I mean, it's kind of crazy. If I add like 3 red points, it looks like this if you do isomap. Like isomap degrades immediately.
Well, appropriately picked at 3 points.
3 random points. Most of the time it degrades. It's really bad.
well, it depends on how big the cube you put this in.
Okay, yeah. If the cube concentrates so that they're kind of near. Fair point. You know, I'm cheating a little bit.
With 10%, you get the right answer.
10%, yeah, but I mean, you know, with 3, it doesn't look like this. At 3, almost all the charts look like this. The subsampling, most of the subsamples miss the points, right? I mean, it's the usual kind of thing when you do the bootstrap. Yeah. Anyway, so this is some kind of topological bootstrap. And I think it's kind of neat, again, because it combines optimal transport, manifold learning, and even topological data analysis, assuming you imagine that your charts should look contractible. And it's a use of topological data analysis where what you're looking, you really care about a signal that's in like pH 0 and pH 1 maybe. And so it's, you know, you can hope to understand what it's telling you.
Okay, so maybe I missed
Yeah.
something. I didn't understand why does contractibility matter? Because I thought you
So-
were looking at the persistent homology, and then you could be clustering on the persistent homology.
Oh, you could do that too. I was clustering on, and that's a good idea. We didn't try that. What I was clustering on was just clustering in Wasserstein space. But you could definitely push to persistent homology and cluster there, and that might be nicer, actually. That's a good idea. What I was saying was something else, which is that any of these manifold learning algorithms, because of the way they're set up, because they're looking for global coordinates, you have to essentially be looking for things that are charts, that are contractible. And so you can detect that using persistent homology. Because none of these things will really, or I don't want to say none, there's a big literature, but there are not very many that work well to give you charts that go all the way around a sphere. Usually what happens is the sphere gets punctured and pulled out, and then you look for a chart that covers that. Yeah.
If that map reverted horizontally, will that be clustered together using Weatherspoon distance?
No. I don't, well, if I understand correctly, no, but I'm not sure what I do. If what gets moved.
With the blue part on the right side, the yellow part on the left side.
I mean, these colors are arbitrary. I'm just telling you, like, this just means this lines up to that. That's all.
Yes, so I mean, if the mapping is kind of reverse horizontally,
It doesn't matter.
so they will be clustered together.
I think they'd be different, right? Because if they were reversed, it depends how you reverse. Let me answer this afterwards. I'm going to need to draw a picture to make sure I know what you're asking. So let me move on. Okay, so now I'm going to talk. Do I have time for this? Maybe. I'm going to talk about something else which uses curvature. So, so I was interested in the story here is I was interested in estimating curvature, and estimating curvature was some kind of disaster, and resulted in this sort of interesting theoretical work that we couldn't get to do couldn't estimate reasonably in any data set, and so felt sad. But then one thing that we observed playing around was that you can use, and I'll now talk about this work, and this is work with Abby and Tristan Sadie and Bastian Rieck. There's this observation that you can use discrete curvature, so this is what's called discrete Olivier-Ricci curvature, to figure out which edges are cross-cutting in your embedding. And you can cut those, and then things work better. And it's kind of cool. So it tells you, because you always worry, right? If you have something like, if you have discrete components, or if you have something like the Swiss roll, you worry about the edges and any of these k-nearest neighbor graphs that go across. They screw you up. And it turns out that you can detect them using Olivier-Ricci curvature, and that you can use that to sort of denoise data and get better embeddings. And so let me talk about that for a little bit. So Olivier-Ricci curvature, you can define this, and I will in a second, in terms of the Wasserstein distance. But what it basically is it's a proxy for whether or not something is a bottleneck. If all the paths on this side to this side have to go through there, it's negative. In something like a complete graph, it's positive because you can go any which way. Okay, so people use it for things like community detection. And this is where this comes from. And you can say things, which I won't unless pressed, but you can say things, you might wonder, is this related to the Ricci curvature? And the answer is yes. And is it related to the scalar curvature if you integrate it around the edge? And the answer is yes. It's sort of, you can say what you want. But this is, for our purposes, this is what you need to know. And so here is the actual definition. You take the uniform measure on the people who are one edge away from your node. And on either side of an edge, you have these two uniform distributions, and you take something like a scaled Wasserstein distance between them, or 1 minus it weighted by the weight. So why is this the right formula? I'm not really going to explain. But if you do this, what you end up with is something that converges to Ricci curvature if you're sampling from a manifold.
I'm sorry. Just say what UX and UY are without us having to read it.
Oh yeah, it's the uniform, mu x and mu y, I'm sorry, those are the uniform measures. So you're looking at an edge, and I take x, and now I take all the things that are connected to x, and I take the uniform measure on those. And I take all the things that are connected to y by a single edge, and I take the uniform measure on those, and then I take the Wasserstein distance between them.
Okay, so it's a measure of some kind of asymmetry.
Exactly. And so we have this embedding algorithm where what you do is you look at, for very negative edges in the Olivier-Ricci curvature, and you cut them. That's the algorithm. And it turns out this is a good thing to do. You can prove that under mild, but well, you can decide if they're reasonable, but under mild hypotheses, in fact, short-cutting edges are pretty negative, and good edges are either close to 0 or positive. That the sign tells you whether or not it's a cross-cutting edge. And it's not so surprising, edges across, everybody has to go through them. And there aren't that many of them, relative to the number of good edges. So, so I'm going to skip this stuff, I think, but you can prove this is a sensible thing to be doing. And then you get these cool pictures if you do this, where if you add a little bit of noise and you prune using this criterion, you get these sort of nice embeddings with all sorts of different embedding things. So these first three are manifold learning, more or less. TSNE is doing something a little bit different. This is preserving local probabilistic structure. And you get these much smoother embeddings, including in cases like with holes where most of these things start to fall apart. Right, so one thing that you notice is that most of the standard, because of the way the global optimization step works, if there's a hole, you're in trouble. Now there's a paper, it's interesting, you can think, could I do better if I was willing to use the second derivative, right? All these things are first derivative methods, but you might say, I could estimate the Hessian. Right? That's a thing maybe I could try to do. And there's a paper by Carrie Grimes and David Donahoe called Hessian eigenmaps or something that does this. Laplacian eigenmaps, I guess we didn't test, but that's another one. Hessian eigenmaps deals with holes, theoretically, but as you might have guessed from my tone and from earlier information in the talk, estimating the Hessian is impossible. And so, in practice, it's so noisy that it's a disaster. Anyway, so it's cool. If you do this, it improves persistent homology calculations. I mean, it cleans things up, right? This is a way of denoising your data. And so it improves this. It improves dimension estimate and scalar curvature estimates. Not that those are so good to begin with, as we've discussed, but this is a better way to do them. So you can also do something cool, and this is maybe the last thing I'll say, which is you can do something cool where you use this to change your metric, where you can push points apart if the edge between them has negative Olivier-Ricci curvature. And we do this, I'm not going to don't even worry about what these formulas are. You have an edge weight where you scale by something related to the Olivier-Ricci curvature. And you should think of that as distorting the metric to push things away. And then you can do SNE does this sort of neighborhood preservation, and you can do a variant of that where you use this new metric, this new distortion in your stochastic neighbor embedding, so some variant of that. And what's cool about this is that this let us extend guarantees for when TSNE works. There's these nice theorems by Aurora and Hu and Cathari, and I think there are other people who have, under niceness hypotheses, SNE preserves cluster structure. I mean, we all know lots of examples where it doesn't, but sometimes it does. And you can get a much wider range of applicability of these things if you do this kind of Olivier-Ricci curvature-based distortion first. And you can see that if we take the original data and we add noise, then if we just do this, we get this sort of weird-looking things, and you get much more sensible pictures if you first do this kind of pruning or this kind of distortion and then do the embedding. So this is going too fast, I think, to be sort of useful in the details. But the idea is that using this kind of discrete curvature measure, you can, even though curvature is a tough thing to estimate, the sign is more or less enough to let you know whether or not you're looking at some place where you have a spurious connection in your manifold. This is a little bit of additional data beyond what's in just the metric estimation. And then we did this in single cell, and it turns out like you can get like very nice trajectory inference stuff out of this. This is on, this is from this thing I was talking about, these mouse developing stem cells. Or most of these things, this is just garbage. And and this is fate, which is supposed to be doing trajectory inference, and that's something more reasonable. And if you do this kind of embedding, you also get something that sort of looks reasonable in how it spreads out.
So how do I see in these pictures what's reasonable and what's not?
You can't, and I'm not. This is the usual. This is the usual, right? So it's one of these things.
So you could tell it's the last slide.
Yeah, it's it's the usual thing, right? Like, these like, and I guess I said this at the beginning. Like on the, what do you do, right? On the one hand, like we all know this is bullshit, right? This is a stupid way to analyze data. On the other hand, like.
You're being recorded.
What? Yeah, I know that, but like, YouTube can hear. Like we all know this is a bad way to like projecting into two-dimensional space and imagining that this trajectory means something is a bad idea, and yet we do it. Because what else are we going to do?
So what is a good idea?
I don't know. Right? That's the problem, right? The real thing I would say about like what do you really do? So of course in this case, like what does it mean that this is a good picture and this is a bad picture? It means we know things. We have priors about what the developmental trajectory should look like. And these line up with anchors where we know where they're supposed to go and how they're supposed to differentiate. I just can't explain that in the time allotted. Plus, I don't really remember well enough without a table to show you what's what. But the other thing to say is, what should you do? Probably, really, we do know that random projections, right? Like this, these old ideas of like Tukey or something, right? That like taking lots of random projections, this is called what, exploratory data analysis, is not a bad way to understand high-dimensional things. The real thing you should do is make lots of such dimensionality reduction pictures and ask which ones are at least stable. And that's some of what this sort of subsampling stuff is talking about, is how to understand the stability theory here.
No, it also doesn't seem so bad because whatever the trajectory looks like in the high dimensional space, when you project it, it should at least project to a curve.
Yes.
Right?
Yes. Yes.
So,
That's right. That's
right?
fair.
So you know that it's not completely informative, but
Yes.
it isn't lying.
Yeah.
It's to tell you the truth, just not the whole truth.
Except for just cross.
Yes, I have another, yes. So the last thing I wanted to say is something about, I guess, my sort of perspective to distill on what kinds of geometric data and how should you use geometric data analysis, right? And this is, go forth and be productive. But one thing that my experience has been is that you gotta have a generative hypothesis. You should know what it is that you're looking at. Right? Like I tell you, oh, I have this data and I've subsampled and it's really stable and H7 has rank 41. Like what are you going to do? Right? That's nothing. But the good examples are things where we know what range of curves we should see, what kinds of shapes. Like there's this nice work that came out of, I think originally out of like Raoul Rabadon's lab, where you're looking at evolutionary trees and population genetics, and you're looking for recombination, which means loops. Well, that's something you can detect with pH1, and it turns out that quantities that come up in the persistent homology have names in the population genetics literature. And so like there's a real thing happening there. And that's something kind of cool. And of course, you have to know that the dimension is low. And then the other thing to say is that optimal transport is actually really useful. I think the jury's kind of out about how useful something like manifold learning really is. Like, clustering is useful. you know, and insofar as you think of this as generalized clustering, maybe it's useful. But like how, you know, getting these explicit coordinates, how good is this? How, you know, I don't know. But optimal transport does lots of stuff, and it's because matching is really important. Right? Matching is a ubiquitous operation. And anytime, you know, I was talking to someone about this in the break, like you have, you know, you want to do batch effect correction, that's a matching problem, right? Anything like that. You know, you want to do subsampling and understand how your subsamples, that's a matching, in a geometric sense or a clustering sense, that's a matching problem. So matching is just everywhere. And that actually is a good thing to do, despite certain difficulties with the computational aspects of it. Okay, and that's it, so.